Hello and welcome back. And next on our list here of things we found at the flea market is the Heathkit impedance bridge that we picked up for $5. Another piece of $10 test bench gear. We're doing it down here on the big bench because we have better lighting and better acoustics down here, less echo. At any rate, we're going to take you through repair and cleaning up of this unit. We're going to take this thing apart, get it cleaned up, get it recapped, and run it through its paces and see how it does. So I'm going to open this thing up. We'll take a look. Okay, we've got the lid off of the Heathkit impedance bridge, and this was obviously a kit built by someone. This wasn't factory built. However, he did a fairly decent job. So fair amount of confidence that this probably works. However, we will be testing all of these paper capacitors that are sealed in plastic here. While they're not the waxy type, I'm pretty confident these are actually paper caps. We will of course replace these electrolytics. This one, there's a large dual 1000 microfarad electrolytic down here, but it's only rated at 8 volts. So I think I'll just check that one and see how it goes. The only one that might prove to be difficult, is there's some sort of waxy capacitor down in here. Are we in frame? Let's move the camera here. Yes, there's some sort of waxy paper capacitor down in here on one of the range switches, and I'll have to dig that out, see what the value of that is and if it's leaky. The tubes in this are interesting. These are tubes designed for battery operated radio. They're all 1-volt filament tubes. There's two 1L4s and two 1U4s. These have 1-volt filaments designed to run on a single D cell. This of course has a power transformer in it. These were developed for very quick warm-up, so basically this has instant on. There's no cathode shell in these or cathode sleeve. The filament is the cathode in these tubes. So when you turn these on, they're basically instant on, which is kind of nice. It's going to be like having a transistorized kit. A little dusty in here, not bad. A lot cleaner than a lot of the ones I've picked up over the years. So I'm going to get busy changing out the paper capacitors. When those are changed out, we'll run this thing through its paces and see how it compares to modern test equipment for accuracy and simplicity of use. Kind of curious to see how it does, and if it works out well, we'll have another nice addition to the $10 test bench for a $5 investment and a handful of capacitors. And again folks, it doesn't take a lot of money to buy this equipment. You look around, you find something like this, it's nice and clean, dent and scratch free for the most part. You bring it home, you put a fresh set of capacitors in it, you learn something in the process. It's all about learning, and that's why I picked up that Cushman unit that I did on the last video. It was just curiosity. The guy said it didn't work. I was curious to see if I could figure out what was wrong with it and make it work again. And it actually was fairly simple repair. It was up and running in about half an hour, 45 minutes. I had most of the problems figured out and it was up and going. Starting to lose my voice here. Hope I'm not coming down with anything. We're going to start recapping this toy and see how we make out. Actually, I might test these before I pull them just to see if they're leaky, these green ones. I suspect they're all leaky. And since I just came home with a brand new bag of Sprague orange drops, I'll probably just go ahead and replace them all anyway. We'll see how it goes. The desoldering tool is warming up, and we'll give a couple of these a check. It's fairly obvious all of these caps have to go. This is supposed to be a 0.02, and while the value is somewhere between 0.02 and 0.03, the eye is barely opening on the capacitance test. The eye should open up wide once I hit the right capacitance. Then we go into the leakage test. And from the blinking light there, you can tell that's half its rated voltage and it's leaking. There's 1/3 its rated voltage and it's leaking. That's supposed to be a 600 volt cap. Now this one only goes up to 500 volts, but as you can see, that cap's history. If that one's gone, the other ones are right behind it. I'm not even going to bother testing the rest of them. We're just going to rip them right on out and replace them and then be done with it. The only one I've got left is that oddball looking waxy one on the top, and I suspect it's bad as well. On Let's give it a look. Square wax covered capacitor that's down in here that I can't read a value on. I'll have to look it up in the schematic, but if we look up here, surprisingly, on the tester says it's 0.1 microfarad, and as you can see, the eye is opening up quite wide. So let's give it some voltage checks. I know the voltage in this unit's never going to go above about 150 volts because of the power supply, and that capacitor is not leaking. There's 400 volts. So I'm going to leave that one in there because that's buried, well and truly buried into the switch, and I have too much danger of breaking the switch. If it was bad, I'd go after it, but it's obviously standing up well. I've never seen that style cap before, but whatever it is, it's absolutely fine. Okay, the restoration is moving along on the IB2A, the Heathkit bridge. We've got mostly orange drops replacing the original capacitors. There's still one electrolytic I need to replace. I'm going to leave this one alone. It's only a 6 volt circuit and it should be fine. And thought I'd move on and start doing some of the cosmetic restoration. And we took all the knobs off and began polishing up the front panel, and it started coming out real well, but when we removed all the knobs we ran into a problem. Very early on, like this condenser checker, they use these hard plastic or Bakelite, I'm not sure what this material is, knobs. And as long as you didn't over tighten the screw on these, they lasted for years. This was a very stable plastic. Later, later in life, they went over to this type of knob with the metal insert. And these metal insert knobs were some similar to what was used on like the Heathkit 101 transceivers and a lot of their test equipment. I've got a lot of Heathkit gear that has this type of knob. These stand up well over the years. However, there was an interim period where they used all plastic knobs like these. And these used to be like in the Heathkit grid dip oscillators, and they failed constantly. They didn't, I don't think, understand fully the plastic that they were using. This plastic degrades with time. Certainly under tension it fails because it's quote-unquote plastic material, and it moves over time until eventually develops stress fractures, and then it becomes absolutely unserviceable. This knob had been glued on, and it is just a series of fractures and certainly won't hold on the shaft anymore. This one seems to have survived intact. There's no fractures on it, so this one I'll be able to reuse as is, and you can see I've polished it up a little bit. They're starting to clean up nicely. However, this knob, as you can see, is completely broken away where the set screw goes. It's, now incapable of holding anything. And these knobs are part of the calibration. You put it on the shaft, you use a known high tolerance resistor, very tight tolerance resistor to calibrate this, and you have to move it on the shaft. And without being able to use a set screw, that's going to be impossible. However, I think I have a fix. I have a box full of knobs, and these have the brass inserts in them. I have several different sizes, several different styles. I even have, that's not it. I have a small one that if this one should fail, I can repair this one with as well. It has the smaller diameter insert. What I'm planning on doing is fixturing this up and cutting out the center web. And it fortunately has a deep enough recess where these knobs can drop in. And I'll either fill this with fiberglass resin or epoxy. I'll align the screw that's in this to match the hole that's on the outside of the knob. Put a small plastic tube there to keep the epoxy from running into the set screw hole. And fill this with fiberglass resin. Then I will have a knob that has the metal insert with a set screw and should last a lifetime. Fortunately, again, this knob is deep enough that it will accept that inside it. This one goes through a hole that's nearly this diameter. In fact, we can show you on the face of the unit over here. That knob fits into this recess right here. There's a huge opening where that this knob fits in. So I have access to the back side of it. So I'll be able to cut this one out, and I'll probably, this will probably be the knob I use on here. I'll build up either a fiberglass reinforcement or an epoxy reinforcement, maybe even JV weld. I'll try several things against a sample of this plastic and see what sticks to it well. So that for that knob, this one should fit in here okay. I should be able to repair that one. And should this one fail, I have a knob with a small insert or small hole in it, like the same diameter as that shaft. These appear to be in reasonably good shape. They don't have a lot of stress on them. Plus, they're they're reinforced by the outside, so that boss where the set screw goes in has a reinforcement ring on the outside that holds it together. These did not, and being under constant tension with nothing to hold that in, eventually failed. So that's where we stand. The next time you see this, I will hopefully have these knobs repaired and back together. I will finish up some spots that I've missed on the polishing. I'll get this front face cleaned up a little bit and take a toothbrush and clean the dirt and the grunge out from the grooves. And we'll put this back together and see how it stands up to modern testing. We have one knob repaired and back on the unit. When its companion knob is on top, actually I can stick that on there right now. Just like that. And then we'll put the little pointer. I've got to take this off and clean. I don't know what that is. It's on there. There's a little bit of grunge, but we'll get that off. We may have to take some plastic polish and clean it up, but we'll get it off of there. And here's the process started on the other knob. Now, I was heady with the success of the first one and rushed into fixing the second one and dumped the epoxy in there, and then it dawned on me, light dawned over marble head, that while this other knob, turn the camera a little bit, while this knob over here had a very large clearance hole behind the, going through the panel, and it let me put the screw assembly behind the panel. This one doesn't have that hole, and I totally forgot that. Dropped my core in and glued it in, or started to glue it in, put the epoxy in, and realized I was going to be 1/4 of an inch proud of the surface, and that wasn't going to work because it wouldn't fit behind the indicator. So in panic, before the epoxy set up, I got in there and dug most of it out. So it looks pretty ugly in there right now. But that's okay. I had to cut this a little bit deeper. Now I've left just enough of the center hole so I have an alignment point. And that also sits a little bit proud, about 1/8 of an inch. And I end up being just about 1/8 of an inch proud of the surface now when I have the other piece in there. This plastic is incredibly, incredibly brittle. It smells like polystyrene when you sand it. but it's far more brittle than most of the model airplanes I played with as a kid. This is probably has something to do with age. It's very, very brittle. So I had to grind down the back of the knob, and you can see there's still some epoxy residue on there, but that's okay because it's getting completely covered in epoxy. Now the trick is I have to epoxy this in there, and it has to be perpendicular to the knob so that the knob doesn't wobble around. So I've made a little fixture to do this. I've got this piece here that the knob fits into very nicely. I've got a 1/4 inch piece of fiberglass which will sit down into the center, and that will center the knob so that we don't have run out. Then I have a 1/2 inch piece of aluminum that I've bored a 1/4 inch hole through, and when the epoxy is in there I will set this on top like that. That 1/4 inch hole will keep the fiberglass rod perpendicular to the knob, because you can see the knob fits right flat against the surface here. So that'll hold everything in position while the epoxy sets up, and theoretically when it's all set up and hardened I'll have a fully serviceable knob again. The back side of it will not be pretty, but you're not going to see the back side of it. There'll be just more of the epoxy poured in there when the time comes. So I'm going to go ahead, I'm going to mix up some epoxy, I'm going to pour it in there, set my block in place so that this is nice and perpendicular to the knob, and hopefully everything will turn out nice and flat, nice and concentric, and we'll have a working knob. I hope this comes out clearly visible. This is the knob that I epoxied to the back of the original knob in the unit. This is out of my junk box. It has a metal core that the set screw threads into so that you can lean on the screw a little bit and get the knob good and tight. Remember, the back of this original knob was completely shattered, and you can see the epoxy here where it comes up the sides of the smaller knob that I glued on the back, and I left it clear of the screw so we could get a screwdriver in there and adjust it. So that has cured the broken knob issue, and while it looks a little rough from the back, it's absolutely invisible from the front. And this is the view from the front. This knob has no depth to it because it has a second knob sitting on top of it. So the replacement knob or the repair knob has been epoxied to the back and goes through a hole that's in the front panel. The hole is original. I didn't add that hole. This knob originally went through the panel. This side has had the same treatment. It's had a knob glued on the back. Now there's a little fracture in the center of this one where obviously this knob was pushed in too hard once. This is a single knob. There's not a double knob here, so there was enough depth inside of this. It was hollow inside of here once I cleaned out the broken pieces, and I was able to glue my replacement or repair knob inside of here and the set screws on the front of this one. This smaller knob right here that's used for the fine graduations or the fine balancing of the bridge was not broken. Now you cannot lean on this screw very hard or you will shatter this to pieces. However, since it was intact and not broken, I elected to leave that one original. Should it ever fail, I can always clean out the inside of this and glue in a repair knob in the back of this one as well. It's a much smaller shaft, where this larger diameter knob and the one down here on the other end use 1/4 inch shaft, 0.250 inches, roughly 6 millimeters. This center shaft is about 1/8 of an inch, about 0.125 inches. Now I do have a knob with a metal insert that would fit that, but where this one was intact, I've left it alone. So we'll put this thing back in the case and see how it works. Okay, it's many days later, and I'm wearing my ratty old shop shirt before anybody makes a comment on that. It's getting pretty cold here in New Hampshire. At any rate, how does the Heathkit impedance bridge, actually LCR bridge, stand up to today's world? and what I'm about to say is going to make a lot of people sad or angry. I'm afraid not very well. Back in 1965 is the date on this manual, 65. This was probably a pretty handy piece of gear. Today, not so much. And we'll run you through it, show you what it does, how well it does or doesn't do it, and you can make your own opinion. I do have a lot of Heathkit gear. I have 2 of these Heathkit audio oscillators. These go from sub-hertz to 100 kilohertz, and they're very, very handy. I still often use my Heathkit high voltage power supply right up here. Very, very handy piece of gear. On my bench still also is a Heathkit. Where it is? Get this out of the way. Right up here. There's a Heathkit FETVOM, FETVOM. Very useful piece of gear. And as you see, I saw on my $10 test bench, I've got an ICO voltmeter. And that gear is still very viable and still very useful today. This, however, if you're on a budget and you're buying something for your $10 test bench or $10 test bench, and I hate to say this because I hate to support the Chinese government, this is the way to go. This will do a better job with capacitance. It'll do a better job with resistance. It'll do a better job with inductance. And on top of all of that, it will test diodes, LEDs, and standard diodes, and transistors of just about every ilk, whether they're FETs or bipolar. And it will tell you what they are, whether they're FETs or bipolar, and it'll tell you whether they are silicon or germanium, and will even identify the leads for you. You just hook up the 3 little clips here, push the button, and it'll tell you which lead is base, emitter, collector, or drain, source, gate. And these are under $10. The Heathkit meter, of course, I paid $5 for it. I've probably put another $10 to $15 worth of capacitors in it. I bought 2 new 1L4 tubes to put in it, and ended up taking those back out and putting them into my stock because they made absolutely no difference. Maybe 1 graduation on the meter. They weren't worth the extra expense. So this now has 3 1U4s and something that's unidentified that actually tests as a 1U4, but it was in the 1L4 socket. So this may have all 1U4s in it. And again, I did put the correct tubes in it and run a series of tests. Made no difference. So if you have one of these, the 1U4s are fine.